and for the invitation. It's an honor to speak in this seminar. I'm going to talk about the time quasi-periodic vortex patch solution for the 2D Euler equation close to the Kirchhoff vortex patch. So let me first introduce the model. I'm going to consider the 2D Euler equation in vorticity velocity formulation, where the vorticity here is a scalar function affected by the velocity field, which is divergence free. So can be expressed as the gradient perp of some stream function psi. And since omega is the curl of V, then by applying the curl to this identity, we can relate psi to omega through this Poisson equation. And by simple assumption of the decay of omega, we can determine psi and recover the velocity by means of Biot-Savart law. Now, we know from Yodevich theory that we have a global existence and uniqueness of weak solution for initial vorticities in the class of integrable and bounded function. As a byproduct, if we take a vortex patches, which is the characteristic function of some domain D0, then the flow generated by the velocity field is uniquely determined, continuous, and carries the vorticity. So the patch structure is preserved all the time, and the problem is reduced to track the boundary, the evolution of the boundary, which is a one-dimensional problem. So if we fix a parameterization of the boundary, of the patch boundary, the parameterization gonna solve this nonlinear and non-local equation, and which simply says that the speed of a particle located at the patch boundary and the speed of the speed of the boundary at the same point have the same normal component. Roughly speaking, it means that if you have a particle on the boundary, then it's going to always remain on the boundary. The global persistence of regularity was proved by Chemin in 1993, and also by Constantin and Bertuzzi, where they proved that if you start with a boundary sufficiently smooth, C1 gamma, then you can propagate the regularity for all time. Yes. Yeah, now due to the symmetry property of the Newtonian kernel, any radial profile like a disk or annulus is a stationary solution to Euler equation. So the asked question is, can we find a periodic solution close to those equilibrium states? And as a particular case, we may consider rigidly rotating solution where the domain at time t is just a uniform rotation of the initial domain around its center, which I'm fixing it here to be the origin. So inserting this ansatz into the previous vortex patch equation, we find this time-independent equation, which simply says that the relative velocity on the patch boundary is the relative velocity is tangential to the boundary. Now, do we have non-trivial, in the sense non-radial solution? The answer is yes. The first example of non-trivial rotating solution goes back to Kirchhoff. if you start with an ellipse with aspect ratio gamma, then it's going to evolve by rotation around its center with a speed, explicit speed related to its aspect ratio. This is the only explicit example of rotating solution that we know so far. However, other implicit solutions are known. In 1978, there were Dim and Zambuski numerically observed a countable family of rotating solution that they call it V-states. Those solutions are M-fold symmetric, which means that they have the same symmetry as M-gon. And this fact was proved a few years later by Burbria. He proved that if you fix symmetry larger than 2, then you have a curve or a branch of solution emerging from the curve of the disk at some explicit angular velocities. So for m equal to 2, the branch emerges at a 4th, and it's the curve of ellipses. Then you have the 3 folds, the 4 folds, and so on. And the point of bifurcation accumulate at a half. At omega equal to 0, Frankel proved that the only simply connected stationary patch is the disk, and Hamidi extended his result to omega negative, but only for convex domain, and the result was improved by Gomez, Serrano, Park, Shi, and Yao very recently, where they proved that for any domain which is bounded and smooth, outside of this range, 0 to a half, all the patches has to be stationary. So no rotating patch outside this range. In terms of regularity, Hamidi, Matteo, and Verdera proved that the V-states, or the rotating solution, are C infinity, but in a small strip close to the disk. And the result was improved by Castro, Cordova, and Gomez Serrano, where they proved the analyticity of the boundary of the V-states close to the disk. Myself, Masmoudi, and Wheeler, we extended the local branches of solution constructed by Burbria to a global one. And the branch of solution that we construct are large in that when the perimeter goes to infinity, the minimum on the interface of the angular component of the velocity in the rotating frame approaches to 0. And this is consistent with the conjecture of Overman, Wu, and Zabowski. Of course, doesn't completely answer it, where they claimed, based on numerical simulation, the fact that on the limiting V-states, on the end of the branches, the V-states are going to develop angles with 90 degrees angles. So this was the bifurcation from the disks. In 1987, there was a numerical simulation by Kam in his PhD thesis, where he suggested the existence of a second bifurcation from the curve of the disk. So this is the curve of the disk, and this is the curve of the ellipse, and then the 3-fold, 4-fold, and on the curve of the ellipses, the second bifurcation occurs. This was analytically confirmed by Hamidi and Matteo, where they proved that at some value of aspect ratio, those values solve a nonlinear equation in gamma. We have branches of solution bifurcating from the curve of the ellipse. But this time, the shapes has less symmetry. They are at most twofold. And another proof was given by Castro, Cordova, and Gomez Serrano, proving also the analyticity of the boundary close to the curve of the ellipse. Okay. Yes, so there was many recent results in the subject from the bifurcation from the analysts to construct a doubly connected rotating patch, the construction of a rotating patch when a layer equation is set in the disk, and the disangularization of the vortex patches with non-uniform profile, smooth profile, the disangularization of point vortices, and the construction of compactly supported stationary solution. And a similar result was also obtained for other active scalar equation, like the surface quasi-geostrophic equation and the quasi-geostrophic shallow water equations. But the common point of all this solution is that they are stationary in some rotating reference frame. So the natural question that may arises here is, can we find vortex patch solution which are not stationary in any rotating frame? This is the case of quasi-periodic solution. So let me quickly explain what do I mean by quasi-periodic solution. So a function in a some Banach space F is called quasi-periodic if we can find a frequency vector omega in RD and some profile F, capital F, which is a periodic in D variable, such that we can express our function in this way. For D equal to 1, this is exactly the definition of a periodic function. For higher dimension, F is quasi-periodic if the frequency vector is non-resonant, meaning that all its components are rationally independent. The archetype of quasi-periodic function is the superposition of cosinus, or also sine, with a frequency vector which is non-resonant. From dynamical point of view, the trajectory are densely contained in D-dimensional torus, and we say that the torus is invariant and support the quasi-periodic motion with a frequency omega. For those who are not familiar with, let me quickly explain the typical problem that appears in looking for quasi-periodic solution, and which is the small divisor problem. So given a function g, which is periodic in D variables, and with 0 average, we would like to find a function f which solves this equation. So by expanding in Fourier series, we may express our function as an infinite series. And for a long time, people like Poincaré thought that it's not possible to make this series convergent due to the possible smallness in the denominator. So the key idea of Kolmogorov was to introduce the Diophantine condition in order to control the small divisor problem and get only an algebraic loss of regularity. So if omega is Diophantine, then you can estimate in Sobolev space, but with a loss of regularity tau.
Probably it have to be G in the right-hand side, not F.
Yes, yes. Thank you. Yeah, so the existence of a quasi-periodic solution to Hamiltonian system in finite dimensions goes back to the pioneering work of Kolmogorov, Arnold, Moser, and Nash on the persistence of invariant tori for smooth and nearly integrable systems in finite dimension, and then the extension to infinite dimensional Hamiltonian system with application to PDE was implemented by Cookson, Wayne for the wave equation and the Schrodinger equation. The literature of KM theory applied to PDE is abundant, and I'm gonna point here only the case which is has similarity with our context, which is the quasi-linear case, where the nonlinearity is unbounded and has the same order as the linear part. The first result in this case was given by Baldi, Berti, and Montalto for the KDV, and their techniques was adapted to other models like the NLS and the water waves and the 3D Euler equation, but with a force in term. Coming back to our problem, we're looking for a quasi-periodic solution of Euler equation, but close to the Kirchhoff ellipse. So we consider an ellipse with aspect ratio gamma and parameterize it by W gamma. And we are interested in a small perturbation of the ellipse. So we assume that our patch boundary is a graph over the ellipse, and the quantity of our interest is psi, which is assumed to be small. And we can prove that it's gonna solve this nonlinear Hamiltonian equation, where nabla here denotes the L2 gradient, and the Hamiltonian is nothing but the kinetic energy plus omega times the angular momentum. This equation has two important algebraic properties beside being Hamiltonian, is the conservation of the average in space. And this is related to the conservation of the mass for Euler equation. And the second property is that the system is reversible in the sense that if psi t theta is a solution, then psi minus t minus theta is a solution. So we may restrict ourselves to reversible solutions, which are even in t and theta. Of course, here we are placing ourselves in the rotating frame, such that when omega is exactly the speed of rotation of the ellipse, psi equal to 0 is an equilibrium, is a solution. So the first thing to look at is the linearized operator at this equilibrium solution. It has a nice structure. It is constant coefficient transport plus Hilbert transform plus a regularizing operator Q. But Q is not completely diagonal in the sense that exciting the mode G makes appearing the mode minus Q minus G. And this is due to the lack of invariance by rotation around the ellipse, because the cosinus G theta and sin G theta doesn't behave in the same way. So the complex Fourier representation isn't the best in our case. However, if we consider the real Fourier representation, the linearized equation or the linearized operator is diagonal and has this matrix form in the variables alpha n and beta n. And then depending on the signs of the input, mu n minus and mu n plus, we have either harmonic oscillators or hyperbolic repulsor. If they have the same sign, that we have harmonic oscillator. If they have opposite sign, then we have hyperbolic directions. So for n equal to 1, we have a harmonic oscillator for all value of gamma. For n equal to 2, however, the linearized operator is described by a degenerate Jordan block, because mu 2 plus is 0 for all value of the parameter gamma. And this is a major problem that I will be back to it later, but let me continue with the other mode. So for n larger than 3, if we place ourselves on the interval 1 to 3, then both inputs have the same sign and all the directions are elliptic. And this is the stability result obtained by Love. And then starting from gamma larger than 3, degeneracies appear. So at and those points of degeneracies are exactly the bifurcation points from the curve of the ellipse. So as I said, this is the disk. So this corresponds to gamma equal to 1. And then at the first degeneracy occur at gamma 3 equal to 3, and so on. If we are in the interval 1 to 3, all the directions are elliptic. Then from gamma 3 to gamma 4, only n equal to 3 is hyperbolic. All the remaining are elliptic. And then from 4 to 5, gamma 3, 4 to gamma 5, we have n equal to 3 and n equal to 4 are hyperbolic and the remaining elliptic. So the first few are hyperbolic directions. So if we want to get oscillating in time solution, we need to evacuate this degeneracies, the point underlined at gamma n, and also we evacuate the first few hyperbolic directions to get oscillating in time solution to the linear system. And then if I select a finite number of sides from the elliptic direction, I can get a quasi-periodic solution if the frequency vector is a non-resonant. Actually, we can prove that the set of values of gamma for which the frequency vector is Diophantine has asymptotically full measure, in the sense that when nu goes to 0, the set has a full measure. Now, how to estimate is just by applying a Russman lemma, which asserts that if you can find an order K0 star, then yes, so if you can find a K0 star for which the maximum of the derivative is bounded below, then you can get an estimate on your set. So all what we need to do is to check this transversality condition on the vector frequency. And this can be done by arguing by contradiction, leading to some gamma bar and L bar such that this identity is true. And then using the analyticity of the vector frequency, we can deduce that this function is identically zero. And then by using the asymptotic of the linear frequency, the analyticity, and the Vandermonde determinant, we can prove that this identity is not true. It's not possible because the frequency vector is non-degenerate. So by this way, we have proved the existence of quasi-periodic solution at the linear level, and to ask the question, does this solution persist at the nonlinear level? So with Massimiliano Berti and Nader Masmoudi, we proved the following. If you fix amplitude epsilon, which is sufficiently small, you can find a subset with asymptotically full measure, such that for any gamma in this set, you can find an angular velocity omega, which is close to the speed of rotation of the ellipse, and a frequency vector omega tilde, which is also close to the linear frequency at the equilibrium, such that the counter dynamic equation has a quasi-periodic solution. This solution is a small deformation of the linear solution, and the deformation can be seen through the frequency vector omega and also through the remainder R, which is very small compared to the linear part. Okay, now about the proof. So besides the quasi-linearity of our problem, which is expressed as an integral operator with a singular kernel, the small divisor problem, and the lack of rotation close, the rotation invariance close to the ellipse, we have a major problem, which is the degeneracy of the mode 2. And this degeneracy is a consequence of the presence of the angular momentum, which is a conserved quantity. So it is a conserved quantity. And the second fact is that it has alpha 2 linear component. And this is component is exactly where the linear vector, the linear operator degenerate. So in order to overcome this difficulty, the key idea is to fully exploit the conservation of the angular momentum G. And so the key idea is to construct a symplectic diomorphism close to the identity. This is reminiscent to the symplectic rectification in finite dimension. However, here we have to implement in infinite dimension, which is particularly more delicate. So we look for a symplectic diomorphism, which conserve the Hamiltonian structure, and which introduces the angular momentum G as a symplectic variable. The other variable, T bar, is the time impact of the flow on the manifold beta 2 equal to 0. So it's the unique solution of local solution of this equation. And the other variables are the projection on the subspace supplemented to the mode 2. This construction is only local, but this is sufficient to our purpose. Okay. Now, in the new symplectic variables, the new Hamiltonian is independent of beta 2 because alpha 2 is exactly the angular momentum, which is a conserved quantity. And the problem is reduced to solve the problem in the infinite dimensional variable u tilde, and with that in which doesn't see the mode 2. So we fix alpha 2 tilde or G, and then solve for u tilde and recover beta 2. However, if we want to get a quasi-periodic solution, the right-hand side of this equation has to be zero average in time. Otherwise, we have a time growth. So the idea is to subtract the average. And this modification will only affect the alpha 2 tilde direction. But alpha 2 tilde is exactly the angular momentum. So it turns out that this modification is just an adjustment of the angular velocity omega. So at this solution, we are not in the rotating speed with the Kirchhoff angular velocity, but it's an adjustment of it. We're close to it. Now, what is remaining is to solve the infinite dimensional part in u tilde, and as I said, doesn't see the mode 2, so doesn't see any degeneracy. So as u tilde equal to 0 is an equilibrium for any values of the parameter omega and gamma, we may think of writing u tilde as a function of other parameters. So we'll look to the linearized operator at 0. Since in the new symplectic variables are changed only by quadratic terms, then the linearized operator at the equilibrium remain the same. It's unchanged. So we saw that it's a Fourier multiplier. And if we assume that the eigenvalue are bounded away from 0 in some sense, then we can prove that the linearized operator is invertible, but the inverse loses derivative. So the implicit function theorem is out of use. This is why we need to implement a Newtonian method modified by a smoothing operator Sn, where at each step we need to linearize around the previous approximate solution and approximately invert. So the difficulty here is not inverting the linearized operator at the equilibrium state, but at any state close to the equilibrium with a time estimate on the inverse. the starting point is to write the problem in more dynamical system language, more adapted to KM techniques. So we write the Hamiltonian system as a small perturbation of an integrable system given by the linear dynamic by rescaling the variable u tilde. And then the solution will be mainly supported on a finite number of sites, which gives the main part of oscillation. This part can be written in action angle variables, and we have the remaining modes, which we put in the normal variable z. Now, in order to decouple the dynamic of the tangential of the normal part, we follow the approach developed by Berti and Boll. It's a long procedure, but the main idea behind it is to conjugate the linearized operator to a triangular system where we can solve for the angle, action, and then in the normal. So it reduces the problem to inverting the linearized operator in the full space to inverting the linearized operator only in the normal direction. We can prove that our linearized operator has a similar structure to the one obtained at the equilibrium, but this time the transport is variable coefficient, and we have a remainder which is also variable coefficient but of size epsilon. So in order to be able to invert it, the intuitive idea is to conjugate it through several transformation to a Fourier multiplier, completely diagonal operator, and then invert. So the reduction, this is a common point in KM theory for PDE. The reduction is done in decreasing order. We first start with the transport part. This has been recently discussed in several papers, where the main idea is to find a symplectic quasi-periodic exchange of coordinate, such that when the parameters are in some Cantor set, the conjugated operator has a constant coefficient transport part, and we can prove that the lower order part is not destroyed. We still have a Hilbert transform. The regularizing operator Q that we got at the equilibrium, and a new remainder of size epsilon, which is infinitely many regularizing. Then the next step is to reduce the remainder. So we want to find a set of transformation that reduce further and further the size of the remainder. So this is done by a KM scheme. The main idea is to look for a transformation or a diffeomorphism close to the identity, such that in the new variable, the terms of size epsilon, which are in red, disappear. So this is, so we need to solve this homological equation. And under a second order Markovnikov condition on the eigenvalues, we can prove that this is invertible, and the new diagonal part is the previous one, and we add the diagonal part of R, and the new remainder is with a smaller size. So by this way, we completely straighten the linearized operator, and we can invert it and apply a no-schmoser scheme. I'm going to end the talk by a few recent results for vortex, for quasi-periodic vortex patches. With Ahmedi and Masmoudi, we proved that we can construct quasi-periodic vortex patch solution, but close to the disk for most value of the parameter alpha, which determine the order of the model. And Hamidi and Roulet proved that for the quasi-geostrophic shallow water, they have a similar result. When for most value of the Raspi deformation, they get a quasi-periodic solution close to the disk. And with Roulet, we get a similar result. We take advantage of the lack of invariance by dilation to construct a parameter B for which we can get rid of the resonances. And finally, in ongoing, almost finished work, we're proving with Ahmedi and Roulet, we're proving the existence of quasi-periodic solution, but this time close to the annulus. And the parameter here is the small radius of the annulus. This is it. Thank you.